In this section, we'll cover the basics of what it means to live outside of Earth's atmosphere and what kind of new conditions that clothing needs to protect humans from without the benefits of the environment we're used to on Earth. The first thing to consider is that there are many different environments outside of Earth and that each environment presents its own unique circumstances for humans. Immediately outside of Earth's atmosphere is the area that we call low Earth orbit. This is where the International Space Station lives, orbiting around the Earth continually. The station is about the size of a football field, including the end zones, and it's divided up into cylindrical modules that are each dedicated to a different purpose, like sleep and exercise, eating, or lab science. Earth's gravitational pull and the drag from the outer atmosphere act on orbiting objects continually, so the station has its own propulsion systems to keep it in the right orbit. It's actually closer to us than you would think. It's usually between 230 and 286 miles above the ground. That's only about as far as Minneapolis to Madison, Wisconsin, or from New York to Boston. It also travels very fast, about 17,500 miles per hour, which means that astronauts living on station go around the world once every 90 minutes. It's much farther to get to the moon. The moon orbits about 240,000 miles from Earth. In the Apollo missions, it took about 3 days to get there. That's a long time to sit in a tiny capsule wearing a spacesuit. The moon has enough mass to have a significant gravitational pull for humans. Since it's less massive than Earth, its pull is not as strong. It has about a sixth of Earth's gravity. Beyond the moon, things get a lot farther away. Destinations outside of the moon include asteroids and other planets. There are a number of asteroids and comets that have been visited by space probes and landers, but never by humans. One of NASA's current focus areas is on sending humans deeper into space to explore asteroids or even to explore other planets. One likely target is Mars, which is about 34 million miles away at its closest. Mars is bigger than the moon, but smaller than Earth, so it has about a third of Earth's gravity, or twice as much as the moon. One of the first things that comes to mind when thinking about living in space is the effect of different gravitational environments. The Earth is massive enough and we're close enough to it that we experience its pull constantly. Astronauts on board the space station are often described as living in zero gravity or microgravity. In fact, they're also experiencing the pull of the Earth constantly, just like we are, but the effects are very different than they are on the ground because the station is in orbit. When something's in orbit, it's essentially falling all the time. So while there's gravity that's acting on astronauts on station, there's no counterforce from the surface of the Earth, so it looks like everything is floating. One way to think about it is to look at how zero-G or microgravity simulation flights are flown. On those flights, the pilot flies the plane upwards away from the Earth and then turns around and heads nose down toward the Earth. Everyone inside is moving with the plane, but when the plane is traveling with gravity, there's no floor to push upwards on the people inside. So for the 30 seconds or so of free fall, everything floats and behaves as if it were in zero gravity. On station, everything is in free fall all the time. The station and the crew and everything inside are moving together. Because our bodies have evolved for life in 1G, or Earth's gravitational field, living in lower G environments has interesting effects. When astronauts first get to space, it's very common for them to get motion sick. As we discussed in the sensory perception module, the vestibular sense is our body's way of understanding which way it's oriented relative to gravity, and it's detected by a fluid-filled chamber in the inner ear. In a reduced gravity environment, that fluid floats around the same way that everything else does. Because the signals from the eyes and the inner ear don't match, it's easy to confuse the brain, and this can cause motion sickness in the same way that it does in other moving environments where the eyes and the ear don't match. If you remember these two laws of motion from the mechanics of impact section, these become very important in microgravity. On Earth, the force of gravity counteracts many other forces. In reduced gravity environments, humans have to learn to move and manage without the effects of gravity. For example, staying in place means being very careful about not applying forces to other objects unless you've attached yourself to something more massive than you are, like the walls of the space station. Typing on a keyboard, for instance, would push you away from the computer unless you have another way to hold yourself there. Objects that you're working with can't really be put down. They have to be stowed somewhere or attached to something, or they'll just float away. That's true for the body as well. Its shape changes without the force of gravity acting on it. In Earth gravity, the neutral body posture looks something like the anatomical position, a person standing straight up. In microgravity, the neutral body posture is more like this. The head bends forward, the arms float up and bend at the elbow, and the hips and the knees flex a little. It's important to remember that every movement away from this posture requires the crew member to work muscles. For example, in Earth gravity, when we bend down to tie our shoes, we're relaxing against the force of gravity and letting it take us down. In microgravity, to reach your feet, you'd need to do a crunch and hold your abdominal muscles tight in order to stay in place. Another immediate effect of living in space is a shift in body fluids. Astronauts find that their faces and upper bodies get very puffy during their first few days on station. This is because the body is used to pushing fluids up against the force of gravity. When that force is removed, too much fluid goes upward. Astronauts say it feels a little bit like having a cold. Over time, the body gets used to the effects of reduced gravity. Fluids migrate upward during the first few days, but they stabilize over time and redistribute over the body surface. This is partly because the circulatory system learns not to work so hard to push fluids upward. However, this means that when astronauts return to Earth, their system has to readjust all over again. For the first few days or weeks, crew members wear compression pants to help push blood upwards. Otherwise, not enough blood would get to the brain, and they'd be at risk of fainting. Another effect of living in reduced gravity is that muscles and bones are also not experiencing the same kind of force that they would on Earth. An immediate effect is that astronauts tend to grow while they're in space. They get a few inches taller because gravity's not pushing down on their spine and compacting the bones and tissues. Unfortunately, longer-term missions can mean that muscles and bones start to weaken. This suit is an example of one design that's been tried to counteract this effect. It works to pull the body together by applying a load from the shoulders down to the feet. The wearer has to work against that load, and it helps keep more force applied to the muscles and bones. Other loads are missing as well. On Earth, the soles of our feet experience the heaviest load as they support the weight of our entire bodies. They've adapted to this starting from when we learned to walk and have built up calluses and reduced pressure sensitivity so that we're comfortable. In space, that load is removed, and the soles of the feet actually go back to the way they were when we were babies, really soft and sensitive. It takes weeks or months after crew members come back to Earth for their feet to be comfortable walking again. Instead of holding their body weight on the bottoms of their feet, crew tend to support themselves on the tops of their feet. They can use these foot straps, but there aren't many on the station. Instead, they can also repurpose handhold bars like these to hook their feet under and stay in place while they're working. This means that the tops of their feet need to adapt like the soles used to. After a year in space, astronaut Scott Kelly had really thick, rough calluses on top of his feet. Liquids are also difficult in space, which makes managing sweat and other fluids a new kind of challenge. Fluids don't flow or drip in microgravity the way that they do under the force of Earth gravity. They tend to blob together, and they're held together by their own intermolecular forces and surface tension. As astronauts exercise, their sweat drops can fly around and travel through the station. Fluids need to be caught and contained with an absorbent material instead. Because fluids don't flow, taking a shower is a pretty different experience in space. On the ISS, crew use bags of water and do something that looks a little bit more like a sponge bath. Washing your hair involves using a leave-in shampoo and a washcloth. Many crew members opt for a short haircut to make the process easier, but even long-haired astronauts do manage. We've been talking mostly about microgravity, but other destinations have different gravitational environments. As I mentioned, the Moon has a sixth of Earth's gravity. That means that astronauts don't float the way that they do on station, but they're much lighter than they would be on Earth. Because their muscles have developed in Earth gravity, that makes them much stronger than they would be against gravity. However, it doesn't make them stronger against other forces. This may be hard to imagine, but one way to think of it is to imagine an astronaut holding a bowling ball on the Moon. Holding it up against the Moon's gravity would be easier than on Earth because the force of gravity is weaker. But moving it would be just as difficult as it would be on Earth because the ball's mass is the same. On Mars, things are a little heavier in a third of Earth's gravity. Another factor to consider is air pressure. On Earth, our atmosphere keeps gases close, and Earth's gravity helps to create pressure. The space station is a pressurized environment, and gases are held in by the station walls. On the Moon, there is no atmosphere, and the surface is exposed to the vacuum of space. The spacesuit then has to provide the air pressure that we need to survive. So few humans have ever been exposed to a complete vacuum that we really don't know fully what would happen. But we do know that there are at least two kinds of pressure that we need to stay alive and comfortable. First, we need pressure applied to the body so that various body parts and organs stay the right shape and don't expand. Fluids in the body may start to turn to gas if they're not adequately pressurized. Second, our lungs need air pressure to function properly. Unlike the Moon, Mars does have an atmosphere, but doesn't have much air pressure. It has only about 0.5% of Earth's air pressure, but its atmosphere is mostly carbon dioxide, so we would still need to bring our own breathable air. Temperature is another huge challenge in space environments. Space is extremely cold, but the sun is extremely hot. And without an atmosphere or a big planetary mass to keep temperatures more stable, some environments swing between extremes of hot and cold. Crew working on the outside of the International Space Station can experience temperatures that range from negative 250 Fahrenheit in the shade to positive 250 in the sun. The experience is similar on the Moon, but on Mars it's a little more stable, but much colder than Earth. Surface temperatures on Mars range from about 70 degrees Fahrenheit to about negative 250 degrees Fahrenheit. For reference, the hottest temperature recorded on Earth is 159 Fahrenheit, and the coldest temperature is negative 128. In addition to the thermal effects of the sun's rays, in space crew are also subject to different forms of radiation than they would experience on Earth, where radiation is filtered through the atmosphere. The kind of ionizing radiation that crew are exposed to in space, like cosmic rays and solar ejections, is dangerous because it can break down cells and DNA, and it can have both short-term and long-term effects. Habitats in spacecraft usually include some form of radiation shielding to limit the amount of radiation that reaches the crew member, particularly in sleeping and eating areas where crew spend longer periods of time. Crew wear dosimeters to measure how much they're exposed to, which also helps in detecting periods of higher radiation, such as during a solar flare or a storm. Multiple dosimeters are worn during spacewalks so that levels at individual body parts can be measured. The eye is a particularly important area since it's more sensitive to radiation than other body parts. Since the first missions, astronauts have reported a phenomenon where they see periodic light flashes, sometimes streaks of light. It's not clear exactly what causes this phenomenon, but one hypothesis is that it's produced by the interaction of radiation with the eye or the brain. During solar events, crew have reported the ability to actually see cosmic rays. The longer the mission, the more radiation a crew member is exposed to. To prepare for future missions to places like Mars, probes have been used to measure radiation levels that are likely to be experienced. The last space hazard I want to discuss is projectiles. Because there's no air resistance in the vacuum of space, debris from very distant explosions can travel huge distances at very high speeds. Larger pieces can be detected by observation systems and typically would be avoided by getting out of their way. But tiny little pieces or micrometeoroids are very difficult to detect. The space station is constantly exposed to micrometeoroids, and because of their tiny area, they can exert large pressures. They can pass right through your body. The outside of the station and the spacesuit are both designed to absorb the force from micrometeoroids and break them up before they can puncture the airtight surfaces. As you can see from the environmental factors we've discussed here, one of the most important questions for living and working in space is whether you'll be inside or outside an enclosed environment, like a spacecraft or a habitat. The next two sections discuss each of these topics. Living inside is called IVA, or intravehicular activity, and living outside is called EVA, or extravehicular activity.